Good morning, afternoon, or evening, depending on where you are located. My name is Marco Patrignani, and this is the long talk for the POPL paper on the Semantic Expressiveness of Recursive Types, which is joint work with Eric Martin from Stanford and Dominique Devriese from VU Brussels. Apologies in advance for any noise you may hear in the background because my kids are playing somewhere in the house. I'm sure this COVID situation is familiar for many of you. The primary question that motivates this work is the need to understand the relative semantic expressiveness of iso and equirecursive types. To the best of our knowledge, this is still an open question. Answering this question is important for language designers, and for example, we know of people that were implementing a smart contract language and wondered if choosing either formulation of recursive types would be more or less beneficial. Also, language expressiveness is an important topic of research, and we'll see that it is fairly old. By answering this question, we further our understanding of tools that can be used to reason about language expressiveness. So, long story short, what did we prove? We proved that iso and equirecursive types are equivalently expressive, at least when studied in the simply typed lambda calculus. Additionally, we proved that they are equivalent, semantically, to having a fixed point primitive in the language. Of course, one may still want to have type annotations for static reasoning, but semantically, iso-recursive types, equirecursive types, and a fixed point primitive are equivalently expressive. Another of our contributions is the way we prove semantic equivalence. That is, to conclude this fact about two languages, we prove that the canonical translation between the two languages is fully abstract. In the remainder of this talk, I'll focus on two of these points only. I'll say how we proved that iso and equirecursive types are equivalent semantically, and I'll justify our choice of fully abstract compilation as the tool to compare language expressiveness. For this agenda, I'll first briefly recap iso and equirecursive types, then talk about fully abstract compilation, and say how we proved that for a translation between iso and equi. The paper contains the details about the equivalence between a language with a fixed point primitive and iso as well as equi. So, recursive types are typically added to a language by expanding the grammar of types to include the constructor for recursive type, mu alpha.tau, and the type variable alpha, which can be used inside the body of a recursive type. The canonical example of usage for recursive types is lists. In this case, we can define a list of natural number as this recursive type, which tells us that a list of numbers is either the empty list unit or a natural number paired with another list of natural numbers. The latter is represented by the type variable alpha. The natural question that arises once we have defined these types is how to relate a type and its unfoldings. That is, the relation between ln and its first level unfolding, by which we mean just take the recursive type and replace its definition for any occurrence of the type variable alpha, or its second level unfolding, that is, the unfolding applied twice. The initial answer to this question was that these types are equivalent, while other researchers provided a different answer, stating that they are isomorphic. Let us see how these answers affect a language with recursive types. The second answer gives birth to iso-recursive types, and a language with those types has terms enriched with annotations that witness the isomorphism between types. These annotations are called fold and unfold, also sometimes called roll and unroll. In order to define the empty list nil, or the list made of two elements 2 and 1, we need to add a syntactic marker fold anytime we're dealing with a term or a value of a recursive type. So nil is a fold of an in left of unit, and the list 2 1 is a fold of an in right of a pair of a 2, and then another list, so a fold of an in right of a pair with a 1, and finally the empty list. From the typing perspective, we can type check a fold at a recursive type if the inner term has the unfolded type, and we can type check an unfold at an unfolded type if the inner term has the folded type. Semantically, the fold and unfold annotations cancel out. The first answer to the previous question gives birth to equirecursive types, which have no need for any term level annotation, but rather they rely on an additional judgment that introduces type equality. There have been different formulations of type equality, both inductive and co-inductive, and in this work we focus on the latter. The reason, as we'll see later, is that the language expressiveness question is made much more interesting by having co-inductive derivations in the language. We can say that two types are equivalent if they are the same base type, if they are a compound type made of equivalent types, or, and these are the interesting cases, if one is a recursive type whose unfolding can be proven equivalent to the other type. Interestingly, we require recursive types to be contracted. This simple check lets us rule out meaningless recursive types such as mu alpha, which are not inhabited by any value. So what is known about these two systems? Abadi and Fiore proved a long time ago that if a term is typable in a system, it is also typable in the other. However, what can we say about termination in a system? Does it also imply termination in the other? And more generally, how do we compare the semantic expressiveness of two languages such as these? This is what we describe now. Let us start with a bit of history on the subject, which is quite dated as some of the results we build upon are almost 30 years old. First off, we cannot rely on Turing expressiveness. Turing machines have trivial interfaces. They input a natural number and output a natural number. But our languages are much richer. They have higher order interfaces, and in the case of ISO and EQUI, these interfaces are possibly recursively typed. Instead of Turing expressiveness, we can reason about language expressiveness by observing how a term T of interest interacts with larger programs, called program context, over the interface defined by the language in which the term and the context are written in. So, the choice of the language affects the interface over which this communication happens. For example, the interface between terms and context in ISO and EQUI can contain recursive types. So, let's assume we can take the same term in two languages. The question becomes, can the interaction between T and an ISO context be different from the interaction between the same T and an EQUI context? There are two key points that I want to explain in order to clarify why this is a correct way to reason about language expressiveness. The first one is, what do we mean by take the same term T? And the second one is, how can we compare behavior across languages? In other words, is an EQUI context able to interact with T in a way that an ISO context cannot? The way we obtain the same T in two languages is by having a compiler, or rather a simple language translator from a language to the other. However, it is not the case that any translation works. We should only take into consideration so-called canonical or well-behaved translation, lest the result be trivialized. Additionally, non-canonical or non-well-behaved compilers do not really let you consider the same term in two languages. So more generally, comparison of language expressiveness should be formulated with respect to a way of obtaining the same term in both languages. So the choice of the compiler should be taken as part of the question and not as part of the answer. In our case, the compiler we use is the identity compiler that additionally erases fold and unfold annotations when producing EQUI terms. This plays to our advantage since the semantics of the two languages we consider are almost identical. So we are relatively sure that a term and its translation are effectively the same term. Now off to the second point. How can we tell if an ISO and an EQUI context behave differently when interacting with the same term? The way we answer this question is by reasoning about equivalences. Instead of reasoning about a single program, we reason about two programs, both in ISO and in EQUI. So we start with two programs, T1 and T2 in ISO, that we assume to be equivalent. That is, there is no context in ISO that can differentiate them semantically, which means there is no context that can interact with T1 and T2 in the ways dictated by ISO semantics and tell them apart. What we need to prove is that the compilation of these terms are also equivalent in EQUI. So there is no context in EQUI that can interact with translated T1 or with translated T2 and tell them apart. Also, we need the reverse direction. So assuming equivalence of translated programs in EQUI, we need to prove that their ISO counterparts are equivalent. These two directions are called equivalence preservation and reflection. We stated that, but the most mathematically pleasing way to define this is by using termination and divergence. Effectively, two terms can be differentiated by a context if the context can terminate with one term and diverge with the other. If there is no such context, then the two terms are contextually equivalent or observationally equivalent. There could be other options to model program behavior in languages. For example, we could rely on traces as the community of correct compilation and secure compilation does. However, this would give us different criteria than fully abstract compilation, and so we do not venture into these, but we point the interested reader to the paper from CSF 2019, Journey Beyond Full Abstraction, for a summary of what those alternatives might look like. The theory that I just summarized in order to reason about language expressiveness was theorized by Mitchell in the 90s and refined by Abadi and others around the turn of the century. And this is called, nowadays, fully abstract compilation, which formally amounts to the preservation and reflection of contextual equivalence, as captured by the definition in the slide. If we expand the definition of iso and equicontextual equivalence in the definition of fully abstract compilation, we see that we obtain a top-level co-implication, the vertically aligned one, between other two co-implications, both of which state co-termination of terms no matter what context they interact with. So we can use fully abstract compilation to prove that iso and equi are equivalently expressive. For this, it suffices to show that the canonical compiler from iso to equi is fully abstract. So it suffices to take two terms in iso and their translations in equi, which means take the same two programs in equi, really. And proving fully abstract compilation amounts to proving that the interactions over any iso interface reveals as much as the interactions over equi interfaces. Of the two directions of the co-implication, the reflection one is simple, and it often can be proved with methods akin to those used for compiler correctness results. But the preservation one is harder, and we'll see why now. Specifically, how did we prove such a preservation direction between iso and equi? This direction is depicted in the slide. Notice the direction of the implication on the right. We start by knowing equivalence in iso, which is here on the top, and we need to prove equivalence in equi at the bottom. By unfolding the definition of contextual equivalence, we need to prove that for any equi context, we have termination with a term, if and only if we have termination with the other. By symmetry, we only prove one direction, and therefore assume equi C with compile T1 terminates, and we need to prove that the same equi C with compile T2 also terminates. Here, we rely on a cross-language logical relation, a proof technique to carry out cross-language reasoning from equi to iso. But first, we face a problem. We can state when a term relates to its compilation, but what should we relate an equi context to? We have a compiler to translate from iso to equi, but we do not have a way to go the other way from equi to iso. So that is the first bit of machinery we define. This is called back translation, and it translates an equi context back into an iso context. Second, we need to define when two terms, or contexts, are related, which we indicate with the less squig and greater squig symbols. We use two such relations for reasons that will be clear in a second. For now, it suffices to say that we require that the two logical relations we use relate both an iso term and its compilation, as well as an equi context and its back translation. By the relatedness of terms and contexts, knowing that equi C with compile T1 terminates, we can conclude that the back translated C with T1 terminates. Then we use isocontextual equivalence to conclude that back translated C with T2 terminates. And then we use the other direction of the logical relation to conclude that equi C with compile T2 also terminates. At this point, there's a few questions that need answering. First of all, what are the logical relations or logical approximations? Second, what is an approximate back translation? Concerning the former, we say that two terms or contexts are related if termination of one implies termination of the other. Concerning the latter, a back translation is a translation that goes the opposite way of the compiler. So in this case, it goes from equi to iso. However, there is a recurrent qualifier that plays a key role in our development, approximate. And we will explain why do we keep talking about approximate notions. Let's start answering these questions from the first one. We rely on asymmetric logical approximations, which is a form of binary logical relation where the terms to be related are from the two different languages. Additionally, the relation is step indexed. One direction of the relation, so we say that an isotherm underrelates with an equiterm if given that we know that the iso t terminates, so does the equi t. The other direction flips the implication. So we say that an isotherm overrelates an equiterm if given that we know that the equiterm this time terminates, so does the iso one. Now with the second question, what is an approximate back translation? The function that translates context is different from the compiler. The compiler from iso to equi is defined based on the syntax of terms, and this suffices not to lose any information, for example, on the types of the terms that are being translated. But the back translation from equi c to iso c, if we define it on the syntax of equi c, we lose type information because typing in equi is ambiguous. So we can define the back translation on the derivation of C. And here is the interesting bit why we chose co-inductive equirecursive types. The derivation of equi C possibly contains type equality derivations which are co-inductive and therefore infinite in nature. So instead of translating all of it, we approximate this derivation. We realize that it is not necessary to rely on all the information that the co-inductive derivation has, but just on an approximation of this information. As a concrete example, consider the following. We know that equi c with compile t1 terminates in some number of steps n. So if there is any recursive types involved in the reduction, the term and the context cannot possibly access more than its nth level unfolding, because after n steps they terminated. So it is sufficient to approximate the terms to deal with n level unfoldings of recursive types, and we should be able to conclude. The issue that arises at this point is that the approximation level n is not known statically, and we need to provide a back translation that works for any n. So, if we are devising a back translation for a certain index n, can we detect if the terms are dealing with values that represent the n+1 unfolding of a type? That is, can we detect that we have surpassed the desired index n? The answer is yes. We can detect the current approximation index by relying on the types. Specifically, we can generate a back translation that takes an equi context with an equi type, and instead of producing an iso context with the same type, it produces an iso context of back translation type, where the back translation type carries the information of the level of approximation n together with the information of the equi type tau. Formally, the back translation type is defined inductively on the index n, and as we can see in the inductive case for n+1, we have a number of subcases based on equi tau. Notice that all of the subcases present the same shape. They are a top-level sum of a type and unit, and this type maintains the information of the original equi type. For example, the back translation of equi unit is iso unit or unit, and the back translation of an equi arrow is the sum of the back translation of the arrow subtypes or unit. We can see the back translation type as an option type. Anytime we receive something in the right part of the sum, something has gone wrong. For example, we have reached an approximation level higher than what was being considered. With the back translation type, we can reason about the details of the back translation. What is the back translation of unit at any index greater than 0? Given that the back translation type is unit u plus unit, equi unit is back translated into in left of unit. However, this is a concern, as standard logical relations would relate iso unit to equi unit, and we cannot use them in this case. So instead, we add a case to the logical relation, for when we know that the terms are related at back translation type. In this case, we request that either the isotherm is an in-right, or, which is the case at hand, that the isotherm has an additional in-left, and once stripped of that, the inner value v prime is related according to the canonical relation to the original equi value v. The last bit of technicality we need is in order to make sure everything type checks, because after all, we are in a strongly typed language. In fact, the compiler translates the term t of type tau into an equiterm of compiled type. And the equicontext interacts with the compiled term, so its whole has type compiled tau. What is the type of the whole of the backtranslated equi-C? As we have seen, it is backtranslation type for n and compiled tau. But this is a problem, because it is not the case that tau and backtranslation of compiled tau coincide. For example, take mu alpha unit u plus alpha. Its backtranslation at index 1 is unit u plus unit u plus unit. So when creating the isocontext from the equi1, we need to add a conversion function, inject, that makes sure that everything type checks. And that takes something of type iso tau and returns the same term at type backtranslation of compiled tau. So iso t is fed to inject at type tau, which returns the same t at type backtranslated compiled tau, which is now ready to interact with the backtranslated context. This was the last bit of technicality needed in order to conclude our result about iso and equi. And this is in fact the first result we proved. The erasing compiler from iso to equi is fully abstract due to an approximate backtranslation. The paper contains two similar results. One about a compiler from STLC with a fixed operator, which simply desugars the fix into a Z combinator, so it's a canonical compiler and thus fits our framework for language expressiveness. And we have proven this compiler to be fully abstract via another approximate backtranslation. And finally, we went from STLC with fix to equirecursive types by composing the two compiler passes and the two backtranslations. The result I presented here studies interactions over interfaces that can be recursively typed, while the ones I omitted study interactions over simply typed but still higher order interfaces. Going forward, we ask ourselves about even richer languages. Now, concerning System F, we know that universal and existential types are orthogonal to what we studied. Our initial work had System F types, but we dropped them for simplicity. We conjecture this result scales to System F with a slight complication of proofs only. Instead, for System F omega, we conjecture that this result holds for fully applied recursive types. That is, recursive types with all of their kinds supplied and with a star as the final kind. We do not know what may hold for richer languages. However, it is worth noting that many realistic languages have systems that are less powerful than F omega, and that simply supporting fully applied recursive types seems sufficient to tell most programmers that they can choose their preferred formulation of recursive types since they are semantically equivalent. With this, I conclude this talk. All of the results of the paper are similar to what I highlighted now, and they rely on the notions that I talked about thus far. If you have questions, see you at the conference. Or if you're watching this after POPL and you have questions or concerns, we'd be happy to hear them via comments or email. Cheers!